Sorry about Friday, had a family emergency unexpected. Remember, we have a test on this Friday. It's going to cover convergence, all that convergence stuff, convergence, probability, the point estimators, and sufficiency and consistency. I don't think we're max on there. Check into that. You should certainly build a definition. And I won't be putting anything about any details about what we're doing today. It's basically just going to be what are the estimators, what do we know about convergence of probability, distribution, and sufficiency, and stuff like that. You should know the central limit theorem, the law of large numbers, and all that stuff. There is a practice test on the web. If you can do the homework to the practice test, you're going to have no trouble with the test. And Wednesday, I'm going to have a review class. You can, I'll just take any questions you want. So Wednesday is your class, and come and ask questions. Any questions? And yes, you can bring a cheat sheet, one piece of paper, both sides, write on there whatever you want.
We never covered how the likelihood function is.
Well, I did say in a statement, I didn't prove it. I did say that likelihood is related to sufficiency, which is if I give you a sufficient statistic, then you can compute the likelihood function. Other than that, you really don't need too much about it. It's going to be straightforward. Here's a model. Here's find the MLE or something like that. Or here's a sequence of random variables. Does a convergent distribution or something? They're just basic questions. Yeah.
How many approximate the question?
Probably about 3 questions.
3 questions.
Any other questions about the test? Okay, good. So we're talking about the consistency of estimators. That just means, of course, that something converges in probability. The estimator converges. And in general, you can prove that one of 2 ways. You can just go to the definition of convergence of probability and verify it. Or show that it converges in quadratic means. So we know how to do that. You show the bias and variance go to 0, and then you show it. But what we were talking about was, under general conditions, to tell us that the MLE is consistent. And in any given problem, you can always say, here's the model, here's the MLE, and I can say, and let me prove that it's consistent or not consistent. So you can always do this on a case-by-case basis, just by using what we know about convergence of probability. It'd be nice to know in general is the MLE consistent. What we proved last time was that if I look at the likelihood function, and if I look at the true value and I look at an arbitrary other value, and look at the likelihood here divided by the likelihood here, what we showed is that with probability coming to 1, the ratio is bigger than 1. The likelihood's always going to end up being bigger here than here. So the likelihood's sort of biggest is the true value. And that's almost a proof of consistency. It's not quite a proof of consistency for the same reason that in the earlier part of the course I said pointwise convergence is not the same as uniform convergence. To show that it's consistent, in general, we have to show that the likelihood around here, that the maximum of the likelihood outside here is always smaller than what's in here. That involves the maximum value, not just a particular value. So we're not going to do a general proof of the maximum likelihood estimate. So unfortunately, what that means is, for us in this class, it's going to be on a case-by-case basis. If I say, is X bar, for a normal, is the MLE consistent? When you say, well, what is the MLE? It's X bar. Yes, I can show that X bar converges to theta. But in general, the MLE is consistent, just so that you know, if there are regularity conditions that hold, and the 2 main regularity conditions, they're called regularity conditions. These are conditions conditions on the model that the set of distributions we're dealing with has to satisfy certain conditions to get consistency. And the first one is that the dimension of the parameter space is fixed. We did an example last time where as I got more and more data, I added more and more parameters. So in those cases, the MLE may not be consistent. And in fact, that's going to come up a lot in a lot of modern problems we solve where we use lots and lots of parameters. And the other one is that there has to be some sort of smoothness condition. Basically that P of x theta is a smooth function of theta. I'm not going to state that in detail, but basically if I change theta a little bit, the distribution can make change different. And I actually should add a third condition, which I mentioned last time, which is that the parameter is identifiable. Remember what that means? It means that you can't have two different values of theta referring to the same distribution. So that what this condition really means is that theta 1 is not equal to theta 2, but we want these two things to be different distributions. When I say not equal here, I mean that these are different distributions. You could create a family where the same, where you have theta equals 5 and theta equals 7 both correspond to a normal 0, 1. I mean, you could just invent a family like that. And we don't want that to happen because then the parameter doesn't uniquely define the distribution. Now, non-identifiability might seem like, why would you ever have a model that's not identifiable? But it can turn out in very complicated models, you can have non-identifiability coming about in unexpected ways. So it may not be so obvious that the model is identifiable or not. But basically, if these conditions are satisfied, especially this thing, if the dimension is fixed. So the maximum likelihood is a very, very effective technique when you're dealing with lots of data and a small number of parameters. That's the practical application. When you have a lot of data and a small number of parameters, maximum likelihood usually works pretty good. When we get to non-parametric statistics, or in 702, for those of you who looked at high-dimensional statistics, we're not going to be in a situation like that. The dimension could be, the parameters could be huge, and then we usually use other methods besides maximum.
So what do you mean by dimension? Is theta vector space?
Well, think about the normal. There's two parameters, mu and sigma squared. So yes, in that case, it's a two-dimensional vector space because there's two parameters, mu and sigma squared. No, it doesn't actually have to be a vector space. So how do we define dimension? There's an abstract way to define dimension using something called metric entropy. What I'm just talking about here is just think of it as some subset of R. In other words, I mean this is a subset of RD for D fixed. That's what I mean. So the good news is that under pretty weak conditions, the MLE is consistent. But we'll see lots of cases later where it isn't. All right, any questions? Okay, the second thing we want to talk about, this is very important, is that in some cases, in fact in many cases, maximum likelihood is also asymptotically normal. And again, we can verify this in special cases for any given model. We can compute the MLE, and if it's a nice function that we understand, maybe it's a sum or something like that, we could say, okay, we've studied this convergence distribution, so I can prove that it converges to normal. But the question is there a general proof that converges to a normal? And there is, and so what we want to show here is that we're going to show a couple of things under fairly general conditions. We're going to show this converges to a normal, 0, and the variance is going to be this special function of I of theta, which I'm going to define in a moment. It's called the Fisher information. So this is what our goal is today, is to prove this. And along the way, we're going to learn a few other extra interesting facts. And this will also, I'll also mention the theorem that says that if you have another estimator, other than the MLE, it's typically also going to converge to normal with a bigger variance. And that's what I mean when I say the maximum likelihood estimator is optimal or efficient. Okay? So to introduce all this stuff, I need to define some terminology. And this terminology comes up quite a bit. So in particular, there's two very, very special functions that come up in maximum likelihood theory, which are called the score function and the Fisher information. So let's start with the score function. The score function is simply defined to be, so I'm going to write it, sometimes I'll just write it like this. It's a function of theta, but it actually depends on the data as well. I'm suppressing that. The n means it's based on n observations. If I want to be more careful, I'll write it out like this. To show that it's a function of theta, but it depends on all the data. And it's nothing other than the derivative of a log likelihood. So it's just this. And in fact, when it's IID, of course, this becomes a sum. So we know that for a well-behaved likelihood, to find the MLE, what do? We take the derivative of the log likelihood set equal to 0. So in other words, often we find the MLE by solving the equation, by solving this equation that the score is equal to 0. And the reason why, so why even give this a name? Well, because it's turned out in a lot of modern statistics, people realize there's other functions besides the likelihood function, which have the property that if you set them equal to 0, you get good estimators. So this function is actually kind of important. It has a lot of properties that make it so that the estimator is asymptotically normal and so on. So whenever I say score function, just remember it's just this thing. It's just the derivative of the log likelihood. And we'll talk about some properties that the score function has in a minute. So the second function, which is a bit more mysterious, is the Fisher information. And its definition is just this. This score function, if you think about this score function, in one way to think about this function, let's actually draw it. Maybe it looks, I don't know, like this. So it's a function of theta. But keep in mind, it's a random function because it depends on the data. If I give you a different data set, and and I said, here, draw the score function. If you had a different data set, you might get a different score function. If I give someone else a different data set, they would get a different score function. So think of it as a function of theta, but think of it as a random function. It's a function that depends on the data. And at any given point theta, I could imagine if I kept simulating the data at this point, I get different values here. I can take the mean and variance of that. Okay? And that's what the Fisher information is it's the variance of the score function. And notice theta appears twice. It's a very important theorem, and this is the same theta. Because what I'm saying is, I can say, suppose the true value is theta. Now simulate data from that model. I'm going to get the score function, compute the variance of that. Then I can go to a different value of theta, but now I have to do the calculation under that theta. And I can do that for every theta, and you're going to get a function. And that function, which seems a bit mysterious if you haven't seen it before, it's called the Fisher information. It will seem less mysterious later, but basically, as I hinted over here, what we're going to see is that the variance of the MLE, we're going to prove that this is approximately equal to 1 over the Fisher information. So that's why it's called information, because if this is big, we have a lot of information, then our estimator is precise, variance is small. So this is very important because one is it gives us some theoretical understanding of the maximum likelihood estimator. It's going to tell us how this random variable behaves, what its variance is. But it's also a way that we want to know, how do I actually get the variance of my estimator, or standard error, standard deviation. We can use the Fisher information to do that. So, any questions? These are just definitions at this point. So now I'm going to show you some basic properties of the Fisher information and the score function. As before, like with consistency, I'm actually assuming regularity conditions. I think next week I'll come in and actually write out the darn regularity conditions in all the gory detail. But again, it just means basically that the model is smooth and theta and the dimension is fixed. And let's just leave that there. And I want to give you some basic properties. So property number one is that the mean of the score function, remember the score function is a random function. And I can pick any value of theta and say, what would the mean be if this was a true value? So what's the mean of the score function? And again, the theta here are the same here. And the answer is 0. And that's critical to every calculation that follows. That's critical for defining an estimator, a well-defined estimator, is that the score function has mean 0. So let's prove that. And this will also show you, in some sense, where these regularity conditions I'm not talking about. So what does this actually mean? Well, the expected value means the integral. What do I mean by this expected value? I mean the integral with respect to the distribution of the data. So in particular, let's write out the joint distribution of the data is that's the joint density of the data. We're assuming again that the model is correct and that the data were generated from this particular value of theta. And I'm just writing out that the expected value is just the derivative. I'll just write it that well. It's the derivative of log. Same thing. It's this thing here. Well, what we're going to do is say that the derivative of the log of a function is just L is log P, so L prime is just P prime over P. So this is just the derivative of P. Over P. Then there's this P here. And of course, this cancels with this. And now comes the key step. I want to take the derivative and bring it on the outside of the integral. And the question is that valid? And that's where the regularity conditions come in. If you have a nice, well-behaved set of distributions that are smooth and theta and so on, you can switch the order of the integral and the differentiation. That's really what the regularity condition is. But we need one more regularity condition for that to be true, which is that the set on which the density is defined cannot depend on theta. So think of a normal. The normal is defined over the whole real line. It doesn't matter what theta is. But think about the uniform 0 theta. The uniform 0 theta, the range of the random variable actually depends on the parameter. So that's not going to satisfy this condition. So when we're talking now about asymptotic normality, the regularity conditions actually get a bit stronger. That this not only has to be smooth, but the range of possible values that x can take can't depend on the parameter. And if that's true, I can bring up the derivative at the front. And, oops, what did I do? out, and then you p. What's the integral of p? 1. The root of a constant is 0. So that's going to turn out to be a pretty useful fact, that this score function happens to have mean 0. And just to see an example of that, let's do the normal example. So the likelihood is proportional to t. The log likelihood squared. And finally, now the score function, I should really be putting n's on these. That's the score function for a normal. That it might even be useful to rewrite this as n times x bar minus theta. And just multiply and divide by n there. First of all, what's the mean of this thing? 0. Right? So now you can see the mean of the score is 0, but the point is that that's not an accident. This happens in every model. But also, this shows you what a score function looks like. If I were to draw this as a function of theta, it looks something like this. But you can see again that it's a random function. If I gave you another data set, you've got a different x bar. It would be shifted up here or shifted down there and so on. So it's a random function. That's the function, though, you're setting equal to 0 to get the MLE. That's how you get an x bar is the maximum likelihood. Any questions? The expectation is with respect to x.
So for given theta fixed on all values,
Right.
then you have to expect over all the random variable x.
That's correct. The expectation is with respect to the x. The only thing random here is the x.
Why is it interesting to have Fisher information and the score function? Like, why
You're going to find out. So you're going to see in a few minutes that these are going to be critical for what we're going to do. So right now I'm just sort of, they seem like they're pulled out of thin air, but you're going to see that they pop up automatically. And in fact, let's go back to the Fisher information. I said it was the variance, but one thing we've just learned, this was defined to be the variance of the score. And we just saw that the score has mean 0. And what's the variance of something with mean 0? It's just the expected value of that thing squared. So another way to write the Fisher information, you can think of it as just the expected value of the score function squared. Because I could subtract off the mean squared, but the mean 0. All right, that's another property you want to know. Here's yet another property. The Fisher information is based on n observations, but it comes from this log likelihood. The log likelihood is a sum of n things. So it's easy to check that the Fisher information is actually equal to n times the Fisher information based on a single observation. That just comes from the definition that they're IID and that the log likelihood is the sum of n independent terms. It's a variance of the sum, so it's the sum of the variances. Now, what I'll usually do is the Fisher information based on a single observation. That means, what does that mean? It means take the score function based on one observation only, sample size 1, and compute the variance, or compute the expected value of that square. If I do that for one observation multiplied by n, that's the same as computing the Fisher information based on n. And in fact, I usually omit this. So if I write the Fisher information with no subscript, I mean the Fisher information from a single observation. We'll do a couple of examples in a minute. This just simplifies the calculations a lot. Instead of having to carry around n observations, just pretend you have one observation, compute this function, and then the Fisher information you get just by multiplying by n. That's another sense in which it behaves like information, that as you get more and more data, the information adds up. The information from n observations is n times the amount of information from one observation. But here comes one of the most important and useful properties of Fisher information, which is that there's a computing this expected value of this variance can sometimes be a little bit difficult. So there's an alternate formula that usually gets used, which is that the Fisher information can also be computed as follows. You take minus the expected value of the second derivative of the log likelihood. So there's two ways to compute the Fisher information. You find the score function and then compute its variance. We'll do, as I say, we'll do a couple of examples in a minute. But an alternative way, and what usually gets used, is you take the log likelihood, we take the second derivative, then you take its expected value. Usually expected values are easier than variances, and then take minus that. And actually, I can do this based on one observation and then multiply it by n. And that's how we're going to actually compute the Fisher information. Why is this true? Let me just sketch out the proof here. In fact, I'll do it for n equals to 1. Because we know how to do it. Just multiplying it by n, we do it for n. So it's the same kind of proof we just used here, which is, and I'm going to just leave out the x theta just to keep it simple, that we start with this basic equation, and then I take the derivative of both sides. That's 0 on this side, and then I bring the derivative on the inside. That's what I did up there, right? And we can prove this, so we get that p prime equals to 0. But I can do the same thing again. If I differentiate both sides with respect to theta, this is 0, and assuming I can bring the derivative on the inside, that tells me that p double prime, these derivatives, remember, with respect to theta, not x. Okay, and now it's going to be helpful if I multiply and divide by p, because then I can think about this. This is like the expected value of this. So this is telling us that the expected value of p double prime over p is 0, and we're almost ready to do the calculation. Let me also write L for log p. Again, I'm suppressing all the x's and thetas, so otherwise it gets very tedious to write all that down. So the score function, again, is L prime, which is p prime over p. And we might as well compute L double prime, which is, I'm just going to differentiate this. So I'm going to get p double prime over p minus. So there's a bunch of identities that I've just thrown up there, but let's see, I'm going to use these identities. They all come from interchanging derivatives and integrals, or at least beginnings of them. So the variance of the score, that's the Fisher information, well, that's the same as the expected value as the score squared, because it, you said earlier. All right, but the score is this. So that's the expected value prime over p squared. That's equal to now I'm going to subtract how do I know I can do that? Because the expected value of p double prime over p is 0. We already said that, right? So this is 0. So I can subtract this. I've just subtracted 0. And that's precisely minus the expected value, if I just bring them together. Which is this. So, just a bunch of calculations, nothing deep happening. But it's a good thing to remember. We're going to use this formula for two things. One is to actually do calculations, but also to prove things. All right, so to summarize, the score function is the derivative of the log likelihood. The Fisher information is the variance of that thing, but it can also be written on this way. That's the key facts. That's what we're going to do. I've done everything assuming theta was scalar, you may have noticed. But in the vector case, when theta is actually a vector, the same stuff is still true. So let's say theta is a vector now. It's a multiple theta. Well, everything's the same, right? The likelihood, our definition of likelihood doesn't change. The likelihood is still just the p of x given theta. And the log likelihood is the same, it's just the log of the likelihood. The score changes a bit. The score was the derivative of the log likelihood with respect to the parameters. More than one parameter, so now we have to compute the gradient. So now you have to think of the score function as a vector. It would just be the derivative of the log likelihood with respect to theta 1 down to the derivative of the log likelihood with respect to theta. So the score function is actually a vector of functions. But everything we proved about it still goes through. So it still has mean 0. It's just so when we say mean 0, I mean that you get 0, 0, 0, 0, so you get a vector of zeros. And the Fisher information, there's two ways to compute it. I can compute, this is a vector, so I can talk about its variance covariance matrix. So I n of theta, which is the variance covariance matrix of that vector. But the same proof we just did works for the vector case. So there's the alternative formula looks like this. It just involves the matrix of second derivatives. It's just, if I look at, so this is going to be a k by k matrix. And if I look at one entry, say the RS entry, that's just going to be minus the second partial derivative. L. So everything is just what you think it would be. It's just the vector version and matrix version. Now we have a score vector and the Fisher information matrix. Everything's exactly the same. So let's look at an example. Actually, let me look at an example. It's not in the notes. Then I'll put one that's in the notes. Computing these things is just routine. It's just a matter of just putting derivatives and so on. So let's do the Bernoulli case. Let's say x1 to xn is Bernoulli p. And we know that the likelihood looks like this, where S is the number of heads. Now the log likelihood is S log p plus n minus S log 1 minus p. So the score function is the derivative. So it's S over p minus n minus S over 1 minus. And you can check that it says mean 0. So to get the Fisher information, the easiest thing to do, you can try it both ways, but we're going to use the, I'm just going to take the derivative of this. So in other words, the second derivative of this what is that? It's minus s over p squared plus minus n minus s over n minus p squared. Did I do that correctly? Let's see. Anyway, did that right? Keep an eye on this because I'm just doing this out of my head, so I could be making a sign error somewhere. And then according to what we showed over there, the Fisher information will be minus the expected value of this guy, of all of this, which is equal to, well, the minuses cancel out. What's the expected value of the sum? NP, right? And it's plus, and this is n minus NP. So that's n over p plus n over 1 minus p, which is n, well we know it's going to be n times something. And then we get, I guess it's just n over p 1 minus p. There you go. And that's how you do all of them. You just write down the likelihood, the log likelihood, the score, take the derivative again, take minus, take the second derivative minus, take the expected value, just kind of do some calculations. Later in the course, when I teach you something called bootstrap, you can see that we can completely avoid all of these calculations. But for now, it's good to know how to do it. So this is the Fisher information. And p 1 minus p. Notice that the score function is random. It depends on the data. The Fisher information function, we took an expected value. There shouldn't be any data left here. This is just a function of the parameter. So there's the next example here, example 11. You'll notice that the notation is a bit weird because I wrote a normal mu gamma. In other words, I'm using gamma instead of sigma squared. The only reason why I did that was it can be a little bit confusing when I start writing second derivatives and there's squares flying around. So I didn't want to get things confused, so I just called that gamma. And this is one you can check. I've written it all out for you, but you should check it. You take the log likelihood, you know how to do that. If you now just take the score function, it's just a derivative, so it's very simple. It's just this. And so again, notice that it's a vector, and you can check that the mean of each of those components of the vector is 0. It's a random thing, mean 0. And then a very, very good exercise to do is now get the second derivative matrix. So you have to take the derivative of this with respect to mu, and the derivative of this with respect to gamma. And the derivative of this with respect to mu, and the derivative of that with respect to gamma. It gets a little bit messy. Now you take minus that and take the expected value of each of the 4 things in that matrix. And it turns out, again, the calculations are there for you. This is what you get. It simplifies quite a bit. So it turns out that these have mean 0. That's not usually the case. The 0 here is, in a Fisher information, is not something you necessarily expect. For the score function, yes. For the Fisher information, it just happens to simplify here. These off diagonals happen to be 0. And these are not 0, clearly. This is n over gamma, and n over 2 gamma squared. You could substitute gamma, take the gamma and replace it with sigma squared to make it look more familiar with the 1. Let's do that, actually. If I had done it in the original, usual parameterization, it would look like this. This is the way you would normally see the Fisher information matrix. Okay, so you're probably still wondering why do we care about these things? Right now, I'm just showing you how to compute them. Right? Given any model, and we're still in the parametric world again, we know how to compute the score, the Fisher information, or in the vector case, the score vector, the Fisher information matrix. Just brute force calculation. And what I want to do is now show you why we care about those things. Let me see, are there any questions just about the definitions or how to compute them?
Or maybe this is a thing for later, but as you said, we have to like impose an extra condition of regularity, which is that, you know, the values of the data, possible values of the data can depend on the data. So do these concepts of any usefulness in the case where the data does depend, or the values of the data?
No. So if we're dealing with the uniform zero theta case, this is like, the reason why that example shows up all the time in statistics courses is precisely because it's a counterexample to all these nice regularity conditions. So we know, for example, that the MLE for a uniform zero theta is consistent. We proved that. But it's not asymptotically normal. In fact, we proved the limiting distribution of some weird thing. It was n times theta minus theta converged to some exponential distribution or something like that. So that's the perfect example of where the range of the data depends on theta, and none of this stuff, the score and the Fisher information are useless for those situations. We're only dealing with what I'll call well-behaved parametric models at this point. Any other questions? In fact, let's put them to use now, because now the reason why we developed all these definitions was for a reason, and here it is. We're going to prove now one of the key results of maximum likelihood theory, which is that under these nice regularity conditions, we have a central limit theorem, which is root n theta hat minus theta converges the distribution to a normal. I'll do the univariate, well, actually no. This is the multivariate case. I use the univariate case. We're going to prove a central limit theorem for the maximum likelihood. And this variance is 1 over the Fisher information. Or if I were to write it intuitively, it's like saying theta hat is approximately normally distributed, centered at the true value, with variance 1 over n. Or if you prefer, I can write this as 1 over n. Now again, on a case-by-case basis, you don't need to know any of this theory. Right? If I talk about the Bernoulli model, in the Bernoulli model, what was p hat? Which is the sample unit. And if I said, well, find the limiting distribution of x bar here, well, you just apply the central limit theorem, right? You know how to do that. Or if I said, find the limiting distribution of some function of that, you use like the delta method or something. So we know how to do it on an individual basis already. But what we're trying to do here is say, in general, the MLE has this very nice central limit theorem. Before we do that, I just want to mention something else we're going to prove along the way. We're going to prove that the MLE actually has a very interesting form. It turns out we can think of the MLE as being the true value plus an average of some function plus smaller order terms, where this function, which is called the influence function, is just the score function for a single observation over the Fisher function. The reason why I wrote this down, it's not critical to what we're about to do, but because I wanted you to see why we're going to get a central limit theorem. Because what we're saying is that theta hat can be thought of as the true value plus an average. And averages, of course, by the central limit theorem, converge to normals. So along the way, this is actually what we're going to end up proving. And it's from here that I'm going to get the central limit theorem. In fact, as it turns out, any well-behaved estimator has this expression, but with a different psi function, a different influence function. But the influence function with the smallest variance is the maximum likelihood. That's why people like to use maximum likelihood. All right, but let's prove this. This is like a really, really central result. And when we talk later about confidence intervals, which are more important than point estimators. Confidence intervals are when I'll give you an interval and say this interval traps the true value 95% of the time. It's a much more useful thing than a point estimator. A lot of the times we're going to compute these confidence intervals using this fact. This is what allows us to get interval estimators instead of point estimators. So when you look at nature or science and somebody is reporting scientific results, they never just report a point estimator. They always report an interval estimator. And they're using this. Or for that matter, right now when you look at these election polls, they don't just say so-and-so is getting 63% of the poll. They say, if you look at, especially the New York Times is good about this, they'll say 63 plus or minus 4 points. And they're using basically this calculation here to get that plus or minus 4 points. So this is all over the place. All right, so we'll start the proof. You probably have to finish it next week, but we'll at least get started. And I'm going to prove it in the univariate, that is the single parameter case. The proof for the multi-parameter case is the same, but it's just a bit messier. And we start with the following thing. We know that if I take, we'll assume that the log like this is very well behaved. And if I take, therefore, the derivative at the MLE, then I'll get 0. That's our basic beginning fact. We're at the maximum, so take the derivative will be 0. Now what we're going to do is expand this log likelihood function around the true value. So I can rewrite this as the derivative of L, the true value, plus theta hat minus theta times the derivative of this function, which would be the second derivative at the true value. And I'm actually going to stop there and say approximately. Doing a really rigorous proof of this is actually quite long, because we have to show that the part that we're going away is negligible. And we'll just proceed heuristically. Now, what I want to do is isolate this term. So I'm going to bring this to the other side. In fact, I'll bring this to the other side. Multiply by root n and divide by this. So what I get, root n, theta hat minus theta, is approximately equal to 1/2. I'm going to write it like this. I just split up the root n term into a 1 over root n here and a 1 over n here, so it still comes up to root n. Let's call this a over b. And before we go through any details, let me now just give you the heuristic explanation of why we're going to get the result we have. What is this? This is a sum. What is that? That's the score function. What's its mean? 0. So this looks like, if I take something, an average with mean 0, I can rewrite that as like that, but that has 1 over n in front of it, so I can write this as 1 over n. So I know if I have a mean 0 thing, and I have a sum divided by root n, that's going to converge to a normal. That's precisely what I have here. So this is going to converge to a normal with mean 0 and some variance. But what's the variance of the score? And look at the bottom. The bottom looks like minus 1 over n, a sum. The second derivative, you can change derivatives and sums. The log likelihood is a sum of n terms. So this is the second derivative of log likelihood, or if you prefer, the sum of the second derivatives, and it's times 1 over n, so this is going to converge to its expected value. The expected value of the second derivative minus sign in front is also going to change. So when we put it all together, we're going to get a normal, mean 0, there's going to be some, let's keep track of how many different informations there are, but there'll be a 1 over different information. So you can see that, I'm going to do the details next week, but you can see that the definition of the score, the definition of the Fisher information, That's why they were defined, is because they just pop up naturally when we're trying to find the distribution for that. So what we'll do then next week is we'll finish this proof, and then we're going to put it to use. We're going to see how we can use this. Any questions? All right, so remember, Wednesday is just a review class. Just come with the questions. And the practice test, we'll post it on the website.